Okay, this is the section for week 12. The answer key and the zip file for the stuff that we'll do after are on Courseworks. So want to just start by going through the answers. Too big? No, it's about right. Okay, so I think I had more trouble on question 1 than I was hoping for. It's pretty much the same as what we did before with multivariate normal. So anytime you're thinking about doing a hierarchical model where parameters have priors that are functions of other unknown parameters, you just want to start with the likelihood, and in this case, complete data likelihood, and work your way out until there's nothing left to express prior information about. So the basic part of the likelihood is that the complete data vector is distributed conditionally multivariate normal with mean vector mu plus W gamma and covariance matrix W times sigma. So the complete data vector consists of some observations, some data points that are observed, some data points that are missing that you're also estimating their marginal posterior distribution of. If it makes it easier for you to think about, for the elements of XC that are originally observed, this is just a plain likelihood. And for the elements of XC that are missing, this is your prior for the missing values. It's just, because it's multivariate, some people are missing on some variables, not on others. It all gets combined together into one thing that Rubin calls the complete data likelihood, which, if you think about this as something that you would construct before you see the data, like ostensibly you should, then you don't know what observations are going to be missing or observed. You just are expressing your belief that all of them follow this data generating process. And then in terms of working your way out, you need to express your prior beliefs about all the parameters in the conditional likelihood. And so starting with mu and gamma, those two are vectors and they can be any real numbers. And so, typically we would go with something weakly informative here. It can be difficult with this distribution to estimate precisely the separate contributions of mu and gamma, but really all you need for the purposes of creating imputations on the missing values is their sum, or you got to multiply gamma by W. If you can get a precise posterior distribution for mu plus W gamma, then you have a high amount of certainty as to what the conditional mean is. And then, that's mu and gamma. For sigma, as usual, it makes the most sense in Stan to decompose that covariance matrix into a diagonal matrix of standard deviations and a Cholesky factor for a correlation matrix. And then since sigma is deterministic, given delta and L, whatever prior beliefs you have about delta and L imply some prior distribution about sigma that doesn't have any additional error since this is identity. So that, working our way out, that pushes back the question, well, what are our prior beliefs about delta and about L? For delta, these are standard deviations, kind of. They would be if W was always equal to 1. In any event, they have the property that you can scale them by a positive number. And that just changes the units of the x variables, which seems like that should not be relevant information for imputing them, in which case the Jeffreys prior for the diagonal elements of delta would be pretty appropriate. And I think that's probably what most people chose. But if you happen to have some good prior information, maybe you had data on these variables from a previous study or something along those lines, you could use an informative prior for the diagonal elements of delta, depending on how much information you have, or basically working up from Jeffreys prior to an exponential prior, which has one parameter, to a gamma prior that has two parameters, to a generalized gamma that has three parameters, etc. But in this case, it's just simulated data, so you don't have any basis really for having an informative prior about delta or much of anything else. So Jeffreys prior would certainly be fine. Turning to L, we want usually the only distribution for a correlation matrix that anyone really knows of is LKJ. So we want to choose the prior on L that implies L times L transpose is not only a correlation matrix, but a correlation matrix that has the LKJ distribution. That's going to have a shape parameter eta, pushes back the question of what to choose for eta. And typically, if you don't have any other information about the problem, you would set eta equal to 1. And that implies that L times L transpose is a correlation matrix that's distributed jointly uniform among correlation matrices of size K. So that basically closes off that branch of the logic dealing with the covariance matrix of the complete data. So back, or that closes off the part about sigma. The prior for W, in this case, it's asserted to be a generalized inverse Gaussian distribution. You can do mixtures of multivariate normal distributions with pretty much any scalar parameter, and you can get some pretty crazy stuff. Generalized inverse Gaussian is a pretty flexible distribution, but you can use other flexible distributions for positive parameters, and you could do them in stand. In order to have a prior that has a unique form, it's necessary, and it's also convenient to restrict the generalized inverse Gaussian prior distribution to have a mean of 1. And so in general, the generalized inverse Gaussian distribution has these shape parameters psi and chi. But if you impose the restriction that the expectation a priori has to be 1, then that reduces the number of free parameters. And as explained in the problem, you could write psi and chi as conditionally deterministic given this positive parameter alpha bar and order for the Bessel function lambda. Anna?
What's the Bessel function?
It's a physics thing. It can be written as an integral that we don't have a closed form expression for in general, but computers can approximate it pretty well. R can do it with a real lambda. Stan, for some reason, it was restricted to only being able to use integer values of lambda. I think for non-integer values of lambda, the Bessel function may involve complex numbers internally, which Stan doesn't do. It can't currently auto-differentiate a complex number. So I think that's why it may be restricted to real numbers. Okay, so if that is a prior distribution for W, and we're going to restrict it to have a mean of 1, pushing back the question, well, what should we choose for lambda? What should we choose for the prior distribution of alpha? Knowing that lambda needs to be an integer and alpha needs to be a positive parameter. And so the problem asserts that lambda is an integer between 1 and 10, basically has 0 probability of being anything else. And that probability distribution is governed by a probability mass function that has simplex parameter pi. So pi is going to be of length 10. The elements of pi are going to be non-negative, and all the elements of pi are going to sum up to 1, which makes it a valid probability mass function for the unknown lambda. Pushes back the question, well, what are your prior beliefs about pi? And for a simplex parameter, the most common prior on that is the Dirichlet distribution. And the Dirichlet distribution has hyper parameters that are often called concentration parameters, and people usually choose the vector of concentration parameters to be proportional to some positive constant. That makes the Dirichlet distribution symmetric. But moreover, if all of the concentration parameters are equal to 1, then that implies a joint uniform distribution over the simplex pi. And since you don't have any additional information about the problem, then it would be quite reasonable to use a joint uniform distribution over pi. But the same thing would result if you didn't put an explicit prior on pi at all. That just means Stan doesn't add any term for the posterior distribution to account for pi, and that's proportional to adding the logarithm of 1 to the posterior distribution, which doesn't change any of the proposals, doesn't change which proposals are accepted, and consequently doesn't change the posterior distribution. Probably the most unsatisfactory aspect of choosing prior distributions for this is trying to choose a prior for alpha bar. You know it has to be positive, but since this is simulated data, you don't know really anything about the data generating process, and moreover, alpha bar is not something that's really easy to interpret. And so in a situation like that, you definitely want to make your prior beliefs be pretty weakly informative. There is something in the vignette for the multivariate hypergeometric distribution that talks about, well, what's the limit as alpha goes to 0? You can get something along the lines of a multivariate student T distribution for small values of lambda, and for larger values, it kind of functions like a degrees of freedom parameter a little bit. In any event, you need something that's positive, but you probably don't want to put too much information into it. So, you know, a half Cauchy might be reasonable, but nothing is really unreasonable except a prior distribution that puts positive mass on the negative numbers, because you don't know anything about it. So that closes off everything. We have our likelihood. We have our beliefs about the parameters that go into the likelihood. We have beliefs about all the hyperparameters that are related to the parameters that go into the likelihood, et cetera. So we just have to express that in a Stan program. So I was attempting to make the problem not super complicated. So I put in the text of it that you could just calculate the PDF of the generalized inverse gamma distribution, and conceptually that may be a little bit easier to do the mixture thing, but in practice it seemed that created a numerical complication with some people having a hard time getting it to initialize. And so the better way to do it would be to implement a function for the logarithm of the generalized inverse Gaussian distribution. And that allows you to use the more numerically stable log sum x function to mix over lambda. But what a lot of people seem to do was just, make a function that calculated the density of the generalized inverse Gaussian internally, and then in the last line, they just took the logarithm of that function and returned it out. Well, that negates like 75% of the numerical stability, because one of the reasons why you get problems with this function is that, it goes too close to zero or too much negative, too much positive, and e raised to the power of something either overflows or underflows. And so if you're going to implement this in terms of the logarithm of the generalized inverse Gaussian distribution, you need to apply the logarithm symbolically and then express the density in terms of the of that. So I didn't write down the density again. In any event, it involves like psi divided by chi raised to the power of lambda over 2 multiplied by something multiplied by e raised to the power negative 1/2. Again, something involving psi and chi and w and whatever. So when you symbolically apply the logarithm to that, you get, the logarithm of lambda over 2 times the logarithm of the ratio of psi to chi plus, some other term involving a logarithm minus 1/2 when e to the log cancels, etc. Gotcha.
About lambda over 2, why doesn't stem like integers divided by 2 or like by numbers?
So C++, is defined operation known in computer science as integer division. So basically, it's restricting when you divide one integer by another integer to return integer. And so if you divide 1 by 2, it's going to return 0 rather than 1/2. And so basically, when you write stuff, you never want to divide anyway. It's just slower and it causes, problems like this. So in this case, it would be easy enough to get around just by multiplying half of lambda, 0.5 times lambda. In that way, if lambda is 1, 0.5 times 1 is 0.5, the real number. And in addition, I think if you work it out, you could cancel the 2 in the denominator anyway, because psi over chi involves the square of everything. Ben?
I was just going to ask about when you're specifying priors in stand, it seems like general feedback I'm getting is that it doesn't really matter how, like you can specify sort of a range of different forms they could take on, as long as, say, it's, a non-negative prior or something of that nature. How do you know whether the prior you're specifying is reasonable for the data that you're then going to run the model through?
Right. So it's automatically unreasonable if your prior doesn't match the sample space of the random variable you're talking about. And pretty much everything beyond that could be reasonable. There's, degrees of reasonableness when talking about real data. In the case of simulated data, then basically reasonable is like binary. Either it has the right sample space or it doesn't. If these variables had names, then we might have prior beliefs about whether this variable is skewed or whether this variable has more kurtosis than a normal distribution or something, and that could imply more information that we could use when formulating priors. I think in the context of multiple imputation, your quantity of interest is essentially the marginal imputations of the missing data, and those are going to get used in some other context, maybe by some other person. So in a multiple imputation context, you probably don't want to put real strong priors on anything, even if you had some reason why you thought those strongest priors were reasonable. And I might contradict myself a little bit when we get to the last problem, where we do feel maybe as if we know a little bit more about the data generating process when we can talk about variables that we actually have names like gender and age and stuff like that. But for the most part, with multiple imputation, you want to get a reasonable complete data likelihood and not implausible priors. And more generally, as long as you have a not implausible prior and a reasonable amount of information in the data, it's not going to matter that much what your priors were. Where the priors can make more of a difference is when you start dogmatically ruling stuff out that probably shouldn't be ruled out. And so, for example, if you do multivariate normal imputation, you're ruling out the possibility that the variables could be skewed, ruling out the possibility that they could have kurtosis, and you probably don't have much reason why that would be the case, and you may even have reasons why that should not be the case. And in a situation like that, it behooves you to use a likelihood for the complete data distribution that has more flexibility. And then with that flexibility is going to come more parameters that you need to try to have some kind of reasonable prior information about. So,
just one other thing there. You said strong priors. What do you mean by strong priors?
I would say the strength of a prior can be quantified best in terms of information. And so we talked about, probably like the third or fourth week of class, different ways of categorizing priors. And one of the ways that we talked about was in terms of entropy. So entropy is a measure of how close a distribution is to a uniform distribution. And so that's, one of the reasons why we like the LKJ distribution for correlation matrices with shape equal to 1, because that implies basically a prior distribution over correlation matrices where every correlation matrix of that size that satisfies the positive definiteness restriction is equally possible. So that's essentially putting no prior information that isn't already implied by the definition of a correlation matrix. For these weakly informative things, those are situations in which it's not possible to achieve a proper uniform distribution, but we might use things like the Cauchy that has extremely long tails in order to not rule out the possibility that one of these variables may be extremely skewed and have a value of gamma that's very far from 0. There were other things that we talked about in terms of reference priors and stuff like that back in the notes toward the first month of class. But I think nowadays you're seeing more and more people use, a normal distribution with like a standard deviation of 10. So that basically is going to put a probability 0.95 that, that thing is between -20 and 20. And so for coefficients of regression and stuff like that, that probably covers, pretty well what would be reasonable values for things. Just to take a quick look at the code for that. So we have the logarithm of this PDF, psi and chi are local parameters within that function. So basically a function is just like another local block where you can declare things, define things, and then return whatever you want to. You just have to specify what it is. In this case, it's a real number. And here I've sort of analytically gone through the density, applied the logarithm, pulled the exponents down, changed the multiplications into a additions, change the divisions into subtractions, etc. I've ignored the logarithm of 2, which appeared in the denominator somewhere. And then the rest of this, I think, is pretty much what we said. You just need to pluck elements out of either the observed x vector or the missing x vector, depending on the value of r, put them all together, multiply by, or multiply the square root of w by delta and L to get the Cholesky factor of the covariance matrix. And then you have this mixture business where for the 10 possible values of lambda, you compute the logarithm of the PDF for w given alpha bar, and then you add to those log densities the log of the simplex, do the log sum exp function, and I put that again here. So you want essentially the logarithm of the sum of 10 densities. You can express by basically distributing out the logarithm of that as the logarithm of sum of e raised to the power the log of pi plus the log density. And then you can pass in log pi plus log density to the log sum x function, and it will evaluate that without having too much numerical problems. Tara?
Sorry, why did you comment out the log of 2 minus log of 2?
Because it's a constant that can't affect whether some proposal is accepted or not, because it doesn't depend on any of the unknown parameters. So it would just slightly slow things down to calculate. Yeah, well, it's speed, but you know, I would never write wrong code just so it could go faster. It's you know, the fact of the matter is that log of 2 is going to appear in the Metropolis acceptance thing for both the proposal and for the current value. So it, by construction, makes literally no difference to what gets accepted and what is not. And so at that point, you're free to make things go a little bit faster. I could have calculated that constant once and used it over and over again. It wouldn't have made that much difference. So anyway, just roll that. In my case, it was necessary to increase the target acceptance rate in order to get rid of most of the divergent Hamiltonian transitions. Your data set was random, and so it may or may not have exhibited that problem to the same extent, but I got a dependence plot that looks like this, which is pretty much what we want it to look like. Certainly for a lag of like 4 or 5, it seems as if that dependence is close to 0 throughout the whole post warm-up period. We do a test, standing at 5, we get, you know, p-values that are well away from 0. So we fail to reject the null hypothesis that all 8 chains have the same multivariate distribution of everything. The missing values, the W, the mu, the gamma, delta, L, all that. That basically covers question 1 and 2. Are there any more issues with that? Okay. Amelia, much simpler to run. You can do it in like 1 line there at the top. But it makes the assumption that the data generating process has no skewness and it has no excess kurtosis. And so in your case, the data generating process actually did. And we can compare the mean that Amelia estimates to the posterior distribution of the mean that we got from Stan, and you can do this comparison a variety of ways. I made some plots like this for each of the 5 variables. So the smooth line is the posterior distribution of the mean vector. mu plus gamma times W. And then the vertical line is the point estimate implied by Amelia averaging over its bootstrap things. And again, yours may have looked different because the data sets were different, but the data sets were generated in a way where there may well be skewness or in kurtosis. And the fact that the Amelia assumes that away means that it can get estimates of the mean vector that are not right when the data generating process really does have skewness or kurtosis, and consequently it's doing its imputations based on those means. I mean, those are marginal means. They get shifted over a little bit for each observation when you condition on the data that is observed for that person, but in general, it's using means that are not appropriate when those means are estimated under the sort of pretty dogmatic simplifying assumptions of the multivariate normal. So you may well have gotten something that's qualitatively similar to that. And there's a lot of people that say, multivariate normal imputation is not so bad, even if the variables are not multivariate normal. And some people would go so far to say multivariate normal imputation is not so bad, even if the variables are discrete. Some people would go so far to say it's not so bad, even if the variables are nominal, which is just ridiculous. But, you certainly can construct data generating processes with, even though the variables are continuous, if you get a sufficient amount of skewness and a sufficient amount of kurtosis, you can make multivariate normal imputation be sufficiently bad. And you would have a hard time convincing someone that I know a priori that all these variables are going to be multivariate normal. Now, you could do some transformations in Amelia, and that might help, but that kind of pushes back the problem of what transformations to do. So I think it's a bit easier to, instead of trying to transform things to be multivariate normal, to change the likelihood to be more flexible to accommodate variables that have, skewness or different amounts of kurtosis or something. Tara?
So if we shouldn't say a priori that it's distributed normally, how can we say a priori that it has some X extent of kurtosis or skewness?
Well, you should always try to achieve more flexibility. This would have, if there were no skewness or kurtosis, then you should get a posterior distribution of gamma that's close to 0 and a posterior distribution of W that's very concentrated near 1, in which case you would basically be maybe a little bit less precise, but this is not inconsistent with the data generating process. It's multivariate normal. It just gives it an opportunity to encompass a wider set of data generating processes. Okay, so that's Amelia. Question 4 is about imputing when the variables have different types, ordinal, continuous, binary. This one pretty much directly what we did in section last time. The only thing is, so you gotta get the R variables attached onto your data set. You gotta make sure that those are coded as ordered factors. Otherwise, MCMC pack will consider the 1s and 0s to be real numbers and give you real imputations rather than integer ones. Also, in this case, you needed, a pretty different tuning parameter relative to whatever we were using last Friday in order to get Metropolis acceptance rate of the cut points for the ordinal thing to be, around 20% or so. But you could fiddle around with that to get pretty reasonable acceptance rates. And then the easiest way, I think, to go about, getting completed data sets and doing, Gosha?
How does this, so in MCMC mixed spectrum now, how does this MCMC 2000 and C 1000 work together? Because doesn't it mean that you have to only two observations?
Yes.
Okay. So
But I have 2 observations on 8 chains. So that would give me 8 or 16 imputed data sets. I actually only wanted 1 draw, but it wouldn't let me do a thin of 2000 with the MCMC of 2000. So I basically got, I ran the burn in for a while, probably honestly not long enough, because if you look at a GIF sampler in general, it's going to have very high dependence out, hundreds or thousands of lags. But I just took a second of my draw from each chain to make my 8 imputed data sets. In any event, making the imputed data sets is easier if you use the replace function that I put on the CourseWorks, and that basically allows you to input the original variable that has missingness and the appropriate number of imputations, where the appropriate number of imputations is equal to the number of missing values that the factor originally has, which in this case is 25. And then we can do that 8 times to make 8 completed data sets. We have to just do that for each variable. And so the first variable is continuous. So I just replaced the NA values with the draws from the posterior distribution that end with the string x1. You could have just put in numerical indices there. That would be fine. It's just a little bit more clever. X2 is a factor. And so we use the replace thing. We pass in the X2 from the original data set that has the NAs, and we're going to supply it with 1 imputation for each of the 25 values that are missing on that. Basically the same thing with Y, and then return the whole thing as a data frame. And now we have 8 completed data sets that don't have any NAs in them. And you can proceed to estimate a quote unquote substantive model on that. In this case, the substantive model is asserted to be Y is a function of X1 and X2. Since Y is ordinal, it'd be reasonable to estimate an ordered logit model. And basically, it's the same code that we did in section. The only thing is you have to append the cut points onto the coefficient estimates when getting the point estimates. Then you can average those point estimates to get even more pointy estimates and get standard errors for those. In this case, only X1 is the coefficient of that is the only one that's estimated very precisely, but that was just me. Your data set may have had different coefficients and standard errors, but should ultimately get those using the same code. So questions about 4 or 5? All right, 6. 6 is hard. And 6 is hard because of the missingness. And 6 is hard because of what, the goal of doing a poll is, which is, more to make predictions than to, try to estimate the causal effect of being, 1 year older or something like that. And, there's something like 7,000 observations, and 2,100 of them are either missing on gender or age or region. And the sampling weights, yes?
Just out of curiosity, is that a real poll, or did they really not answer the gender question that often, or did you make it missing?
No,
It's
real poll.
missing?
Yeah, the only thing I changed was in the want to win, there was, one of the answers was like both third party and don't know were combined to one answer category. So there was Obama, Romney, third party don't know. And I changed the third party don't know to missing. But no, other than that, it's a real poll. And there are a lot of people who, Google knows if you're a woman, but there are a lot of people who don't want to give out, you know, personal-ish information on, you know, internet poll stuff. You know, if you do face-to-face polls, you would get a whole lot of missingness on income. Ironically, if you do online polls, you know, people are willing to at least put down some answer for that, but they seem to be not willing to put down anything that, you know, maybe Google could sell, or I don't know. So the sampling weights are really important because the sample is not at all representative anyway. Among people who answered the gender question, it's like 70% women. So they like taking surveys, but don't like answering any of the questions about them. I don't know. So in order to, you know, make an inference to the population, need to have sampling weights, and like 2/7 of your sampling weights are missing. And moreover, the people for whom your sampling weights are missing may be systematically different in their political preferences than the people whose data are less missing. So you can figure out what weights Google was using, using a regression and logarithms with full interactions between these things. So they did not weight by income or urban density, only those three. But in any event, we need, you know, the main thing we need to get is the sampling weights. If you just talk to someone who studies American politics, they could give you a pretty good idea as to what is the probability that this or that type of person is going to favor the Democratic candidate over the Republican candidate. Like, they could probably do it within, you know, 0.02. Like, that's something that American politics people have extremely strong prior information about. But they would be, you know, a lot more uncertain as to, you know, what type of person is this, just based on the limited information that we have. And so you basically need to create the variables inclusive of the R variables, make them into a list. And then you need to write a JAGS model that has a likelihood contribution for each of the variables. So if any of the variables have missingness, then that has to be modeled, and a likelihood contribution for the corresponding R variables in order to not make the assumption that the data generating process is missing at random. And it seemed like a lot of people, for the part of this that pertained to the R variables, were just, you know, using like some constant, or, you know, unknown constant that they were estimating, you know, of the probability that you don't answer the income question or whatever it may be. And that kind of defeats the purpose, because if you say, you know, missing this is a function only of an unknown constant, then that is to assume the data generating process is missing completely at random. And if you could assume the data generating process were missing completely at random, then you could just use the complete cases. So you really need to think hard about, you know, a model for the which category people are in on these variables, and to think hard about what sorts of things might cause people to be missing on some of these variables. And you can, and in some cases it's reasonable, to model one R as a function of another R. So, you know, one of the enduring patterns that we often see in the data is that, you know, people who don't answer the age question are also, you know, the type of people who are less likely to answer the region question or something like that. So you can specify those likelihoods of R's in terms of R's, as long as you don't create a cycle. And in that case, DAG wouldn't be able to estimate your model. And so basically these, what I did, there's a lot of things that could be done. Pretty much followed along with the way Jackman writes JAG's code in his book. A lot of these variables were ordinal, and so we have like a CDF thing going on. People were using logit models, and that's fine. JAGs ought to be a little bit faster if you use probit models and multivariate normal priors, because those are going to be conjugate sometimes. The region variable, some people were trying to model that as ordinal, which does not make sense. There was a part in Jackman where I talked about a multinomial logit model, which would be more reasonable for a variable like region, or if there were a race variable, a variable like race. That basically involves normalizing the mu's in order to make probability of living in each of the four regions.
All these things and avoid cycles. What's like the way of going about this? So for example, if we try to predict, let's say we say, well, income is definitely correlated with gender. Do we want to predict then gender by income or income by gender? I mean, do we think about causality then, or
right? So, well, no, we don't want to think about causality in basically a predictive framework. And so basically it shouldn't matter too much, I don't think. So if you have a marginal distribution for income and a conditional distribution for gender given income, gender and income. And if you do it the other way with a marginal distribution for gender and a conditional distribution for income given gender, which probably makes more sense in a causal thing, then again, you end up with a bivariate distribution of that. So you could do it either way. I don't think it would make too much of a difference. You just gotta, do something reasonable for all those margins. I think the easiest way to ultimately answer the problem is to make an additional, what JAGS calls a node of the posterior predictive distribution. So here is the likelihood for the want to win stuff. And then just right under it, I make what JAGS interprets to be a new variable, the posterior predictive distribution, that I'm just drawing from the same thing as my likelihood. And so when JAGS returns, it'll just give me, for all in observations, a draw from who they support that could then use to construct the weighted means. So for the cut points, sometimes you need starting values to get JAGS to get going. That's all fine. In any event, you get a coda object that you should probably analyze whether this converges, but the only pieces that you need are the posterior predictive distribution, gender, age, and region, because the sampling weights are only a function of gender, age, and region. And so basically, for however many draws from the posterior distribution you take, can iterate over those, make a local data frame where you take the part of the draw that starts with the letters PPD, make that into the one variable, the posterior predicted distribution of want to win, grab the gender variable, the ones that start with gender, the ones that start with age, the one that starts with region, and now we have a data frame with 4 columns. We can predict based on that OLS model that I did before to get the log of the sampling weights. E to that tells us the sampling weights, and now we just want to do a weighted mean of the posterior predictive distribution of who wants to win with those sampling weights. And now we have like 1,000 draws for the mean or whatever. And mine came out with distribution like this, which is, basically putting the mode near 0.6 for Obama, which is, 7 or 8 points higher than what he actually got in the election the next day. But again, this poll, it's using sampling weights to weight to the population of all adults rather than all voters or all registered voters or all likely voters or anything that, polls actually do. And so I do think this is probably a little bit high, but it's not, inconceivable that if all like residents or whatever were allowed to vote, and all residents did vote, that you could get upper 50s or something for the Democratic candidate in a national election, maybe. Question?
One thing on confusion. So what Jack gives us back has a variable for every observation that we have in the data set, even if it's not missing, right?
Right. If it's not missing, it's just repeated the same time every iteration.
Yeah, that makes total sense.
I mean, you could do it the hard way too. That's fine. Okay. So turning now to the stuff in the section. Tara, do you have a question about the homework?
Do we have to keep doing next parabolic stuff, like, at the final?
No.
I'm sorry for the question.
I think we're done with JAGs, but it's something that you need to be capable of doing in a pinch, because it is still the best way for dealing with missingness on discrete variables. Okay, BART. So install the package BART machine, and we got that. We're going to do the example that we've done before on women who smoke when they're pregnant and how that affects the birth weight of the baby. So that data set is in MCMT pack. Let me reconfigure. Okay, so we got the birth weight. We need to change the race variable to a factor. Bring in BART machine. BART machine can estimate stuff in parallel, but this is actually going to go pretty quickly. So what are the X variables that we have here? These X variables. So age, race, smoke, some other things about how many times the woman went to the doctor, other variables. But in any event, we're interested in the causal effect of smoking, and we can do that with a continuous outcome. So this is the baby's weight in grams. And so we run that, and it's basically instantaneous. In this case, we don't have any missingness, but if we did, it would be relatively easy to just add, include missing covars equal true, and the other thing that has a real long name, but it has missingness somewhere in it, and it will, do its splitting rules that it has for missing variables. And if we just look at the printout, the summary of it, it'll, tell you some stuff. In this case, it is capable of doing a test for the normality of the residuals. We get a not tiny p-value there, so that's good. Some other basic information about what happened, but it doesn't really tell us anything substantive. So in order to estimate the causal effect of smoking, we can do something like this, where we're going to create a new data set, and come on, shift. Whatever. So we're going to make a new data set called T1, and in that T1, we're going to make counterfactually everyone a smoker, and then predict the outcome in that new data set. And then we're going to go and do the other thing where we make everyone not a smoker and predict the outcome in that situation. And at this point, we have estimate of the treatment and control for the same people. We could actually go in and look at the estimates of the individual causal effects, but in this case, those don't seem too interesting. So we'll just look at the average of the difference in the estimated causal effects, and that gives us a treatment effect of essentially negative 289 grams less does the baby weigh for smoker versus not smoker. So that's how we would use BART, which is ultimately just geared for predictions. But if we can do predictions under counterfactuals, then we can use it for, we can do some other cool things with this, like the interaction investigator. Come on. Go interaction investigator. And we get a plot like this. So it turns out, you know, having a baby is a pretty not linear process. And, you know, there's a lot of these variables, I don't even know what they mean, but they interact with age. I know what that means. And whatnot, particularly the one on the far left, which is interaction of UI and LWT. I don't know what that is, but it's non-linearly related to the weight of the baby. So if this was an interesting question to you, you might be more excited about those interactions. You can also do the covariant importance test. This is going to do permutations to get a permutation distribution of the R squared if it jumbles up the Y values. So you can see, you know, what proportion of the time is the R squared that it estimates more extreme in the null distribution than the R squared that you actually observed in your model. So in this case, you know, it's actually, it's jumbling up the variable that you tell it to arrive at a null distribution. And this takes a second. Any questions about what we've said so far, Tara?
What does it mean that you need the delta SE6 runtime to run Mark?
Yeah, you just told me.
I don't fucking know.
So just install it?
Yeah. I mean, don't install it from some random website. Install it from Oracle, but.
No, they actually suggest, yeah, 4 or 6, like some.
0.04. So according to this, we could reject the null hypothesis that smoking is irrelevant to the baby's weight. Okay. We could do the same thing with a binary outcome. So, or not the same thing, but a similar thing with the binary outcome. So there's another variable in this that's just a dummy. You're like classified as low birth weight according to doctors or not. There's probably some standards for that. Again, it runs pretty quickly and it outputs something known as the confusion matrix, which is basically a crosstab telling you, you know, how many times it predicted the baby would not have low birth weight, how many times it predicted the baby would have low birth weight, and, you know, contrasted that with the actual observed things that you observe. Again, you can do the interaction investigator and the covariance importance test, but we won't go through that. Again, you could estimate the causal effects, in this case, in terms of the incidence of 1 and 0. So this tells us that the causal effect of smoking increases the probability of having a binary low birth weight baby of 0.16. So it's a different causal estimate than 289 grams that we got before. Also, we can use this to illustrate the propensity score method of doing causal inference. So in this case, we want a model of do you smoke when pregnant? And so that involves the smoke variable. Now we're modeling the treatment assignment mechanism, but we don't use the fourth variable, which is the smoking variable, in order to predict that when we're doing our propensity score model. So we run that. We get a confusion matrix for whether you're a smoker or not, but that's not too helpful. What we want for propensity scores is the probability that you are a smoker, which we can obtain from that. And then there's different ways to do this. What, a lot of people in the propensity score literature, they just stratify the probabilities into like 5 buckets. So I will make quantiles, and then I will cut the estimated probability of being a smoker into a categorical variable based on the cut points coming from the empirical quantiles. So we have that. And now for each of those 5 strata, we can calculate the means for the birth weight of the baby. So this right here is the stratum for probability of smoking between 0.551 and 0.925. And, here is the stratum for 0.037 and 0.551. In any event, the birth weight of those babies was about, on average, 26. And the birth weight of the babies that were born to mothers that didn't smoke, average was 3405. So in order to get an estimate of the average causal effects, we can just get those differences in each stratum. And those differences are those numbers there. And in this case, since all of these have 1/5 of the sample, I can just take the mean of those estimates, and we get an estimated causal effect of 250 grams lower using the propensity score method. So you can certainly use BART for predictive purposes, and that's what a lot of machine learning people, but it's equally useful for doing causal inference without making assumptions that the data generating process is linear and allowing, arbitrary amounts of interaction between the treatment variable and the covariates. And it can be used, when you don't really have a formal experiment, etc. If you can substantiate a ignorable treatment assignment assumption. So the last thing is to do a Gaussian process model, which is also used for situations where you want a very flexible relationship between the covariates and the outcome. So here, I make a nonlinear data generating process as it relates to X. I could have a vector of covariates. That would be fine. So this data generating process based on the inverse hyperbolic sine function is, very steep relationship near 0, but it gets flat as you get farther away from 0. Estimating that by OLS would just give you, a slope of 0, when really there is a very precise, albeit nonlinear relationship between X and Y. So if we look at the Gaussian process code, just jumping ahead, as usual, you declare your data. In this case, we need additional data based on the differences between the ith observation of x and the jth observation of x. We're going to estimate the smoothing parameters of this Gaussian process. And the model of this is actually pretty simple. Y is multivariate normal with mean vector mu, which we just set to 0, and then some sigma, or we actually called it k yesterday in the slides, where you can make a user-defined function that implements whatever kernel function you want, and you just call that function to produce the kernel matrix, and then it's just multivariate normal likelihood. We have some weakly informative priors on the hyperparameters to that, and then we can generate, the posterior predictive distribution the same way, just by drawing from a multivariate normal that has that kernel matrix. And you can, plug in whatever covariance function, kernel function you like, and just call it build k, and that's the only thing that you have to change. In this case, this is the code that we saw yesterday for the so-called generalized squared exponential kernel function. And it's the same as what we talked about yesterday, so I'm not going to go through it again. Hopefully this will run fast enough to actually see something. Well, that's compiling. Any questions about this? Yeah?
You're trying to get the political scientists. So there's people who always that are very upset about the extent to which causal inference is forgotten theory. It seems like this is a much further I'm just gonna run a bunch of variables and see what happens.
Yeah.
Is that not the case?
No, I would say that is the case. Hurry up.
I mean, in some ways it tells us a lot more about the data, but at the same time, for people who are you should specify your theory, however big or whatever.
Yeah, I think what I would say to that is, yes, you should specify your theory, and obviously I didn't with simulated data, but the theory generally entails what are the variables that go into the data determining process, and are they positively or negatively related to the outcome over the bulk of the range. What's not part, and what's not part of the theory is that this or that variable doesn't have interactions, or this or that variable doesn't have polynomial, or doesn't have this shape to it. Like if somebody said my theory is that y is positively related to x, this is consistent with that theory, but rarely, if ever, does anybody actually say, I have a particular functional form. And in that case, estimating a model with a flexible functional form, but including those variables that are specified by the theory is a pretty reasonable way to go. We don't have any more time, but it converged pretty quickly, and we got estimates of the hyperparameters that, although we don't really care about them, have a pretty large effective sample size, and this basically looked good. And if I did the plot, it would have more variance out here in the tails, and in here near 0, where we have more information about the relationship between y and x, it would probably have narrower credible intervals, and then they would get bigger uncertainty out here again, etc. Okay, out of time today, so let me stop this. Put some readings on the syllabus for next week. We'll talk about some traditional econometric